Hello everyone, my name is Omar Wasim Al Zaidi. Today I am happy to share my research about making industrial networks safer using smart AI models. I worked on this project with Dr. Mohammed Al Hubeishi at Halid University in Istanbul. I am really grateful for his support and I am very excited to tell you about what we found together. Let's start. In this research, we looked at how to solve big security problems. In industrial networks, which are called IIoT networks, our idea was to use two modern technologies together, which is software defined networking or SDN, and the second one is artificial intelligence or AI. We built a system that combines both, tested it, and compared 15 different machine learning models to see which one works best. We also made a real-time threat detection system that is fast and accurate. Our approach used the strength of both SDN and AI to make industrial networks much safer. Let's go to background and motivation of this paper. The Industrial Internet of Things, or IIoT, connects machines, sensors, and control systems to help factories work better. But as these networks get bigger and more complex, keeping them safe is harder. There are more ways for attackers to get in, and lots of different devices and ways of communicating. All security methods just aren't enough anymore, especially since these networks are so important. That's why we wanted to find better way to protect IoT networks. When we looked at past research, we found two main things. First, SDN help with IoT security by letting us manage the network from one place and separated how we control the network from how data moves. This makes it easier to see what's happening and sets up strong security rules. Second, adding AI to SDN helps help us spot strange patterns in network traffic and react quickly to threats. Some researchers also use blockchain and edge computing to make things even safer and faster. But not many have combined all these ideas just for IoT security. So that's what we wanted to explore in this research. This is the big picture, the system architecture of the project. And this slide show how our system works. At the top, there is the SDN controller, which is like the brain of the network. It manages how data move and keep everything organized. Below that, we have our AI security system, which checks network traffic in two steps. First, it decides if the traffic is normal or suspicious, and then it's look closer at any threats. The arrows show how data move from the IoT devices, get checked by the SDN and AI, and then the results go back to keep the network safe. Software defined networking, or SDN, is a new way to control networks. The main idea is to separate the parts that make decisions, the control plan, from the part that move the data plan. So there is two parts of the SDN. This means we can manage the whole network from one place using software instead of hardware. For IoT, this makes things much easier to manage saves to manage and it's make it easier to manage and save money, improve security, and help the network grow and change as needed. Here is a simple look at how SDN works. At the top there is a remote controller which acts like the brain. It tells the network devices what to do by sending them rules. The network is split into two parts: the controller plan, which makes decisions, and the data plan, which moves the data. Each device listens to the controller and follows the instruction. This setup lets us manage the network easily and quickly respond to any problems or attacks. IIoT networks face special security problems. There are lots of connected devices, which means more way for attackers to get in. Many old industrial systems weren't built with security in mind, so they have weaknesses. If these networks are attacked, it can even affect real world machines and processes. Also, because these systems need to work in real time, we can't always use heavy security tools without slowing the things down. All of this means we need special security solution for IoT. This slide shows the 8 most common cyber attacks in IoT. DDoS attacks flood systems with traffic to shut them down. Man-in-the-middle attacks lets hackers listen or change messages. Phishing tricks people into giving away secrets. Malware is software that damage systems. SQL injection puts bad code into database. Zero-day attacks use new bugs before they are fixed. IoT-specific attacks target weak devices, and advanced persistence threats are long-term. Sneaky attacks, all of these can cause big problem in industrial networks. So this is the 8 common types of cyber attacks. The Industrial Internet of Things, or IIoT, is all about connecting machines, sensors, and software to make factories and industries work better. Unlike regular smart devices at home, IIoT is focused on things like safety, efficiency, and reliability. It uses smart sensors to collect data, control system to manage machines and devices to process data quickly, and special communication method to keep everything connected and secure. IIoT brings lots of benefits. For example, it helps predict when machines will break, track equipment, check product quality, save energy, and improves supply chain. But there are also big challenges. Security is a big worry. All systems can be hard to connect. Different devices don't always work well together, and there is a lot of sensitive data to manage. Plus, many companies don't have enough skilled people to set up and run these systems. For our research, we used a big dataset with over 1.1 million records from IoT networks. Each record has 47 features showing different things about the network traffic. The data includes both normal and attack traffic like DDoS and command injections. We split the data into training and testing sets, which is like 80% 20%, to make sure the classes were balanced. We also cleaned the data and picked the most important features to help our AI model learn better. Pre-processing, we make feature selection, normalization, encoding, handling, and missing values. Our system works in two main steps. First, we use AI models called LightGBM and XGBoost models to quickly check if network traffic is normal or not. These models were very accurate. LightGBM got 100% and XGBoost got 99.99%. If the traffic looked suspicious, the second step checks that kind of attack. It may be like DDoS or command injection. This part is closely connected to the SDN controller, so the system can react right away. This two-step approach help us find threat quickly and also understand them in detail. We choose XGBoost and LightGBM because from the over 15 models we compare between them because they are very good at finding patterns in complex data. They use many decisions tree to make smart choices. We train these models carefully, tuning their settings to get the best result and avoid false alarms. In the end, we combined their decisions using a voting system. This was linked to the SDN controller to help make quickly decisions. We focus on catching real threat while avoiding unnecessary alerts. So the system is both smart and practical for real industrial use. This is the methodology for AI model we used, how we implement the XGBoost and Light GBM. How we integrate the SDN for this work. Well, connecting our AI system to the SDN controller was a key part of our work. We set up real time monitoring so the system checks network traffic all the time. If it finds something suspicious, it can change network rules, isolate bad traffic, or even block it. We also made sure the system can balance the load across different controllers so it stays fast and efficient. This makes the whole security system flexible and able to react quickly to new threats. Let's go to the model performance. Our results were excellent. The XGBoost, for example, model made perfect predictions, no mistakes at all. We tested 15 different machine learning models, and XGBoost and LightGBM were the best, both getting 100% accuracy. We choose XGBoost for our main system because it was faster to train and the time efficiency, which is important for real-time use. This means our system can spot and stop threat very quickly, which is exactly what is needed in industrial networks. And for the XGBoost, the time it's 2.91 seconds, and for light GBM, the time is 7.29 seconds. So we choose XGBoost because it's faster in the time. This slide show which features were most important for our model. Our results were perfect. All normal traffic was correctly identified, and all attacks were caught. No false alarms. The system was also very fast, with XGBoost taking less than 3 seconds to process, as we said, to process the data. This means our system can work in real time, which is very important for industrial networks. We also learned which network features are most useful for spotting attacks, which can help design better security in the future. Even though our results were great, we faced some challenge. Some features in the data were similar, which could cause problem. There was also a risk of a class imbalance, which may make the model less reliable in new situations. Training these models can be expensive, and real world networks can be noisy and unpredictable. Also, if the SDN controller fails, it could affect the whole system. This is another problem. These are things we need to keep working on actually. For future enhancements, looking ahead, we want to make our system even better. We plan to use Omnet++ for more advanced threat detection, to make simulation in Omnet++ for future enhancement. We are also looking at federated learning, which let us training model without sharing sensitive data, and making lighter model for devices with less power. We want to use more than one SDN controller to avoid single points of failure. Add explained AI to make the system easier to understand and test everything in real industrial settings. To sum up, we combined SDN and AI to make IoT networks safer. Our system was very accurate and fast, solving key problems like security, scalability, and adaptability. This work shows that using AI with SDN can really help protect industrial networks. So that's all the work we did. Thank you for listening, and I'm happy to answer any question you have.